All right, now we're going to be looking at primary standards. So let's just stop for a second because we have looked at quite a few things here. We've talked about what titrations are, we've talked about the different types of titrations, and we're focusing in on the acid-base titrations here. We said the purpose of titrations was to calculate the concentration of an unknown. They can be simple unknowns such as chemicals in the lab. You've got an unlabeled bottle of sodium hydroxide or hydrochloric acid and you need to work out its concentration. Or they can be slightly more complicated titrations when we want to look at, let's say, the amount of phosphoric acid in Coke or the amount of citric acid in juice. But at the end of the day, you're just finding out the concentration of an unknown acid or base. And when we did that, we started looking at how you set it up with your burette, and in your burette you had your titrant. That was the known solution that you are using to try and calculate the concentration of the unknown sample called the analyte. Well, this video is looking at, well, what is a standard solution and how do you make it up? So let's get into it. All right, so the whole point here is we want to add a known solution to our unknown so that we can calculate its concentration. So the more accurately we know the concentration of our titrant, the better. Well, the titrant here wants to be a substance that has some characteristics that allows us to ensure that its concentration is constant. One example of that is called potassium hydrogen phthalate. Here it is here, okay, and it has one hydrogen that can be released, so it's called monoprotic, and it's a very stable acid that is used as a titrant to determine the concentration of bases. So let's look at some features or characteristics that enable us to ensure that the titrant is a good titrant. Let's compare a good standard and a poor standard. If we want a titrant that's going to do its job properly, it must be pure. Because if it's pure, it means that everything that's in the titrant is what we expect and is going to react with the base as we expect, according to the equation. If, however, we have some impure substances in there, then that is going to affect the accuracy of our titration. Stability. Well, we want to ensure that our titrant is not going to break down and form other compounds, and we want to know that it's so stable that when we place it into the beaker, that it's going to react in a predictable manner with the base according to the equation, that it's not going to react with other things. And so therefore, stability is very, very important. So a good primary standard is highly stable. It has a long shelf life and won't decompose. So you know when you go to use it, it's going to work as predicted. And it has a constant molecular mass. It's not going to change by decomposing on the shelf, and therefore its molecular mass is going to stay the same, which is going to help us with calculations. Okay? And then we look at hygroscopicity. Well, what is that? Well, it's the ability to absorb water from the atmosphere. If something is hygroscopic, it's going to absorb water from the atmosphere. That, of course, changes its molecular mass, and therefore it becomes harder to get a known mass to make up a primary standard. You want to make sure that when you mass it on the scales that you are only massing that compound in the molecular formula for your primary standard. You don't want there to be attached water that is going to affect the mass and therefore the number of moles and therefore the concentration of your primary standard. So we want to choose something that is very resistant to reacting with water in the air. Cost, obviously, we want it to be inexpensive, and molar mass. It wants to have a fairly large molar mass if possible, because the larger the molar mass, the larger its molar mass, then therefore the easier it's going to be mass out. It means that you're going to have less weighing errors when its mass is larger. And so these are some features that we want in good primary standards. These are some examples of some good primary standards. We've got potassium hydrogen phthalate. We can see it's got a large molecular mass there. It's very stable, etc. It doesn't react with water in the atmosphere. Oxalic acid is another example of a good primary standard. Now these are done in red to tell you that these are acid primary standards, and they will therefore be used to standardize bases. So if I wanted to find out what's the concentration of that sodium hydroxide solution, I can use these. I can make up a solution of that, and that will do that job perfectly. These are very poor primary standards. Now, in the very simple titration examples, you see that we do use hydrochloric acid. and sodium hydroxide, right? Because we have that one-to-one relationship. However, normally in those questions we say it has been standardized. So we know the concentration of our HCl very well because we have standardized it with a known base. So we might have used, for example, anhydrous sodium carbonate. We've used that good primary standard to then react with hydrochloric acid and say this is the known concentration of hydrochloric acid. Then we use that hydrochloric acid to then find out the concentration of sodium hydroxide. So this is the primary standard that we use to standardize our HCl. Once we know the concentration of HCl, that becomes a secondary standard, and we use that to find out the concentration of our base. So that's why sometimes when you read questions, it'll say a standardized solution, right? It's already been calculated from a primary standard, okay? Now, sodium hydroxide is very poor to use as a primary standard because it reacts with water in the air, it absorbs water, and also reacts with CO2, and so its concentration is constantly changing. And that's why generally in questions we'll say a standardized solution of sodium hydroxide was used in a titration, right? A standardized solution. It's already been determined its concentration by using one of these. Okay, so now we know examples of good primary standards, poor primary standards. What do we mean by a secondary standard? Okay, so make sure you're writing these down. Secondary standard is a chemical that has been standardized, in brackets, standardized, using a primary standard to determine its concentration accurately. Right, now how do we make a primary standard? Well, this is a little bit going back to year 11. We made primary standards in year 11 in making up a solution. And so remember, we just calculate the mass of solute that we need to make a specific concentration. Then we mass that out, so having a high molecular mass is a good quantity there. And then we of course dissolve it in some water. So we half fill some water, we dissolve it, we put that into a volumetric flask. So one feature I forgot to mention in the last slide was that it should have a high solubility, a good primary standard, high solubility. So all of what you measure will be in solution. Then we put it into our volumetric flask. We then fill our volumetric flask up to the etch mark or calibration mark, and then of course we label it with the concentration and the date that it was made. Alright, so that's how you make your primary standard, and it's ready to go. Alright, so we've covered a lot in this video here. We started off by looking at what are primary standards, why do we use them, and we said that primary standards were used because they are chemicals that are stable, that have high purity, they have a known concentration, etc., all those features that we mentioned, and they are used in titrations because they are reliable chemicals that we can use to determine the concentration of an unknown. We mentioned the concept of secondary standards, and they were chemicals that were not very good at being primary standards, such as sodium hydroxide and hydrochloric acid, and they are because their concentrations change or their concentrations are unknown or not, they're variable. So with concentrated HCl, when we get it, when we buy it concentrated, it gives us a rough percentage of its concentration. So it's not known really precisely, right? And so we want to standardize that HCl by reacting it with a known base primary standard, and that allows us to then use that HCl in another titration. Okay, and then we looked at how do we make up a primary solution very, very quickly, because we have done that previously in year 11. So hopefully that makes sense to you, that now we're getting very close now to conducting our titration, and when we conduct our titration, we'll start off with very simple examples with, of course, HCl and sodium hydroxide, do some calculations, but then we're going to hit you with some harder ones, and that'll get the brain cells pumping. So until then, look at the posters, your study cards, have a go at the Kahoots below to reinforce your knowledge, and I'll see you in the next video.